Okay, so the recording has started. Like I said, these are the office hours, and there's none on Friday. I am going to have a Zoom class tomorrow at 10 a.m., but there will be no new material. It will be practice for Unit 13 and Unit 14. For today, I'm going to try to get, well, I plan to get all the Unit 14 videos up, but we're going to consider this lecture video number 1, where where I'm going to introduce the reactions of benzenes. The notes check for the Unit 14 videos will be tomorrow night, so that will give you a little more than 24 hours to get the notes for the 5 to 7 videos that I will post. The exam on Friday. After the review session, which is going to be from 10 a.m. to around 11:30, I will put on Moodle exam number 4, and you have till the due date to do that. You don't have to be. I mean, I'd rather you're not going to be logged on to Zoom. I'd prefer that you print it, but if you haven't been printing exams the past couple of times, that's fine. I've been able to grade answers on line paper. Let's go to Moodle real quick, just so I don't miss anything. All right. Monday, Tuesday, Wednesday, Thursday, Friday. Okay, so it looks like your exam is going to be due at 8 p.m. There's no late submissions. So if you have work in the afternoon, or if you have plans Friday night, uh, get that get that exam done right after our lecture. It is going to be written as a 1 hour and 15-minute exam. That's normal. I think I might have revised the syllabus. Let me see what this looks like. Not that. Oh, that's not good. How about this? Let me post. I know I wrote up, and I just send it probably by email. But let me just repost it in 1 second. Yeah, in 1 second. Use this time to find your notes for the aromaticity. There's going to be an extra credit in about a minute about aromaticity. Right now I'm looking for the syllabus. There it is. All right. Hopefully you can see my Moodle screen. In this revised syllabus, you all have this. I emailed this to you, but here it says the exam 4 is going to be released at 11:30 on Moodle, and you have till 8 p.m. to finish that up, and that will be it for for the lecture part. Exam 4 will be just 13 and 14. We won't get a chance to talk about nucleic acids, but you'll get plenty of that in your upper level biology classes. Okay. Let me double check. All right. If there are no questions or comments, the extra credit is going to be this. Can everyone see? a second. Great. Hopefully everyone is back onto my document camera. Windows. Okay. So the extra credit, we'll make this for 3 points. And then we'll get to the material for Unit 14. But I just wanted to see how well you understood the aromaticity videos. Let's see. I'm going to give you 3 molecules, and you're going to tell me whether they're aromatic, anti-aromatic, or non-aromatic. Why don't we make this for, well, just 3 points. Your choices are aromatic. We'll do this in order. So in terms of stability, the next class is non-aromatic. And then anti-aromatic is explicitly making that molecule much, much more destabilized than what you would normally expect if you didn't understand this concept of aromaticity. It's the one where it doesn't fit Huckel's number, and when you do that frost circle, you have unpaired electrons normally in anti-bonding molecular orbitals. So it has a lot of things going against it. And if a molecule can somehow become non-flat or change one of its sp2 atoms into sp3, then it's much better because then the molecule becomes non-aromatic. Okay, so the first molecule is this. Go ahead and copy this onto your notes. Okay. 5-membered ring, but I'm going to protonate that nitrogen, so this is positive. Okay. And this is going to be molecule A. Molecule B is going to be the stop sign. Three double bonds only. Okay. So I'm not going to put that 4th double bond. Instead, I'm going to make a dianion. That's molecule B. Molecule C is this one right here. Okay. I think that's molecule C. Everything's neutral. This is molecule C. Okay. Your task, I don't need any explanation, but get this into your notes. And your task is to tell me for each of these whether that particular molecule is aromatic, non-aromatic, or anti-aromatic. How are you going to submit this? Because I don't need to know your explanation, you're going to email me your answer. You're going to type it out on email and send it to me. Email me your answer. And I do want to get this done before we start any new material. So I have 1018. Why don't we make this 11? No, not 11. 10. 1024. Okay, that gives you 5 minutes. Okay. I think that's it. The hint is draw all your lone pairs. I would draw all your lone pairs, okay, and just see if you're going to count those lone pairs as part of the pi system. A, B, and C. All right. So I have, I have 1019. I'm going to check the timestamp on your email, and it has to be 1024 or less for it to count. And you're just emailing me. So get your email open. You're going to email me from your account the answers for A, B, and C. If you get done early, just relax. When we come back, or when I come back, we're going to start Unit 14. Okay. So go ahead and finish that. All right, good. I've gotten 2 so far by email. The rest of you have 3 minutes. Very interesting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4, 5, 6, 7, 8. We're coming down to the last 30 seconds. Okay. we're going to have another shot at this, I think. The answers, well, let's do this. Let's go through these in order. All right, the first one. There's no way that nitrogen can be sp2. If there's no way for an atom to be sp2, then it can't be aromatic, and it can't be anti-aromatic. Because this nitrogen has 4 areas of electron density, and there's no way, you can't make a sigma bond from a p orbital. This is non-aromatic. So this nitrogen has to be sp3. You're automatically non-aromatic. I hinted that it'll be very important that you put the lone pairs. So you know that for these carbanions, each carbanion has a lone pair. The idea here is you want to double check whether the molecule can be aromatic first. And if it can't be aromatic, then you choose between non or anti. So what is definitely a requirement for it to be aromatic? It has to be all sp2 atoms. So this is where you pretend if all are sp2. If all are sp2, okay, let me lower this brightness. If all are sp2, where do you think those lone pairs are? An sp2 carbon looks like this, right? You have that, and you have these 3 sp2 orbitals, and you have this p orbital, straight up and down. Okay. You could even, back to the original example, the first example, you could put a nitrogen right in the middle. You have 4 single bonds. So how can it be sp2? Because you have a sigma, sigma, sigma. The p's don't form sigma bonds. The p's form pi bonds. So you cannot have any of these electrons up here. Okay. So this has to be sp3. What about this? Back to our carbon. Well, you have, if you know what a carbanion is, you have a sigma bond to the carbon to the left, a sigma bond to the carbon down here, and a sigma bond to the hydrogen. So these are your 3 sigma bonds, okay? And one of them is, yes, one of them is to a hydrogen. Okay. So where can that lone pair be? That lone pair can only be in the p orbital. Okay, you could have a single electron in each lobe, or you could have 2 electrons in one lobe. It doesn't matter. Okay, it doesn't matter. That means that both of these, if you want all the atoms to be sp2, then both have to be part of the pi system. 2, 4, 6, 8, 10. There are 10 pi electrons. It's flat. It has 10 pi electrons, and all the atoms are sp2. This is aromatic. Okay. You're going to play the same game with this, because you have atoms that are normally sp3, right? They have 4 areas of electron density. Oxygen has 2 lone pairs, nitrogen has 1. But it's those situations where you have an sp3 atom can conform into an sp2 atom, right? Normally this carbanion would be sp3, correct? But for it to participate in any resonance or aromaticity, you have to be an sp2 atom. But that's perfectly fine for these carbons. It will be perfectly fine for oxygen to be sp2 if it's beneficial. So we play the same game. If O and N are sp2. Okay, I'm not going to redraw the cartoon, but imagine oxygen. You only have 2 sigma bonds. Those 2 sigma bonds will be 1 and 2. You still have 2 lone pairs. So there'd be a lone pair in the P and a lone pair in the sp2. From the video, you saw that one of the lone pairs was sp2, one of the lone pairs, and I'll draw a p orbital like that, as p. So out of oxygen, if it is sp2, That's the only decision you have to make. Everything else is made for you, because if oxygen is sp2, one of the lone pairs has to be part of the pi system. Okay. What about nitrogen? 5 valence electrons, 3 sigma bonds. The sigma bonds are 1, 2, and 3. So that lone pair has to be in a p orbital. So this is in a p orbital also. That screws us, because how many pi electrons do we have? If both O and nitrogen are sp2, then we have 2, 4, 6, 8. We have 8 pi electrons. If we kept it like this, that molecule will be anti-aromatic. But our trend is aromatic, non-aromatic, anti-aromatic. So if there's a way for us to make one of the atoms sp3 to get to non-aromaticity, that's what the molecule is going to conform to. That atom is going to be sp3. It doesn't matter which atom becomes sp3. As soon as one of them becomes sp3, you get out of this really, really bad situation of anti-aromaticity, and you become non-aromatic. So in this case, you know that the molecule cannot have both atoms as sp2, because if they were, you'd be anti-aromatic. So instead, one of these atoms, both, or one at a time, can be sp3, right? And that's what you know from Organic Chemistry 1, that if you have 4 areas of electron density, your atom is sp3. This ultimately becomes non-aromatic. So in this case, we saw that the molecule can avoid being anti-aromatic. That's why it's so important for you to have a list of what molecules can be anti-aromatic, because it seems very easy, right, for a molecule to become non-aromatic by just becoming not flat, or by changing one of its hetero atoms into sp3, into an sp3 atom. All right, so the answer is non-aromatic, aromatic, non-aromatic. This is important in terms of reactivity. Your DNA is made out of aromatic molecules. Your DNA is pretty stable and resistant to any reactions that take place at it's called the basis of DNA. Some of your aromatic proteins, some of your aromatic amino acids are very resistant to reactions also, because again, aromaticity means that your molecule is very, very stable, and it would rather not react unless you have very extreme conditions. Okay. On this flip side, if the molecule is anti-aromatic, it is super reactive. Right? This is very reactive, actually. That was our first example of an anti-aromatic molecule. And when I mean super reactive, you give it a little bit of HBr, this goes like a shot, and you make this molecule here. Because it's so anxious to get out of being anti-aromatic that it will react with HBr. Whereas, benzene, and we'll see today, benzene is not reactive to HBr, but we're going to see today how to make benzene reactive. Okay. So those were all more subtle examples. Okay. Here, because of that nitrogen, you have to know that that's sp3. For this one, you have to know that for this to have any chance of being aromatic, those 2 carbons have to be sp2. And when they are, you are forced to put both of those lone pairs in p orbitals. Okay. Over here, this one's probably the trickiest, because we don't know which one is sp3. It toggles between the oxygen and nitrogen, but one of them has to be an sp3 to avoid this molecule being anti-aromatic, because it has a anti-aromatic number of pi electrons. If you understand this concept, once you decide an atom is sp2 or sp3, the lone pairs are set. Those lone pairs can only exist in one of 2 orbitals, either the sp2 or the p. And that's already decided for you. Okay, once you decide if this is sp2 or sp3. This is always true. That oxygen, if that's sp2, one of the lone pairs would be in p orbital, has to be, and one of the lone pairs has to be in sp2. For nitrogen with 3 bonds, 3 single bonds, if you make that nitrogen sp2, the only space for that lone pair is in a p orbital, because the sp2 orbitals are being occupied by making sigma bonds. Okay. Let me move on if there are no questions about this. I'll try to figure out another extra credit probably today or tomorrow or even Friday. I have that opportunity to give you extra credit during class on Friday as well. But yes, go ahead and keep practicing. Your practice problems are available and the answers are posted already. All right, so Unit 13. The whole unit was basically telling you why benzene is unreactive. Unit 14, we're going to show you how to get benzene to react, but it's going to be under very, very special conditions. So Unit 14. Oh, shoot. You know that you have your video checks due tomorrow night. Why don't you do you and myself a favor, and this is going to be the start of your notes check. Okay? So we'll call this quote unquote video 1. Just so your notes start at the beginning. Unit 14 is simply called benzene reactions. And I'm going to do something a little bit different. I'm going to start out with the roadmap. Okay, and then we will look at each individual reaction and look at the mechanism. The roadmap is this. Okay, somewhere in the middle of your page, there's only going to be 5 reactions. Okay, so we'll need 5 arrows from this benzene ring. And the first arrow will draw it up like this. Okay. How do we brominate benzene? We're going to use Br2. And there's going to be a catalyst. The catalyst is going to be FeBr3. If you want to chlorinate, Cl2 and FeCl3. I'm not telling you anything about the mechanism right now. I just want us to start out with a roadmap so we see the 30,000 foot view of what the meat of this unit is going to be about. And to save space, I'm going to draw it on this side. What do you notice about the answer? We keep the molecule aromatic. We don't lose aromaticity for the final product. During the mechanism, you are going to lose aromaticity, okay, but it will quickly grab it back and become aromatic. So we're going to keep the benzene ring. You're just adding a bromine. So what do we replace? We replaced a hydrogen. Next reaction. We're going to put a nitro group on it. Or you could say we're going to nitrate the benzene ring. You're going to nitrate it with HNO3, H2so4. And we have nitrobenzene. Does that molecule look familiar from your video notes? In Unit 13, we took nitrobenzene and we reduced it to aniline. We replaced the NO2 with an NH2. Okay, so that was Unit 13. Alright, so that's good because now we're trying to connect units together. And to make aniline, the NH2, we take benzene, we nitrate it, and then we reduce it. Okay. Again, I don't want to clutter up this drawing, but we can add to it later some of the Unit 13 reactions. Next one. We're going to sulfonate it. Sulfonate it, there are a couple ways. The most popular way is called Fuming H2so4. Very, very harsh conditions. Very concentrated sulfuric acid. Sometimes it's under a lot of pressure, pressurized, and then heated to high temperatures. Your molecule is going to be neutral. Okay, so don't forget this H right there. Okay. Next. And I'm going to give these names. The names for these three are pretty easy. Bromination, nitration, sulfonation. The sulfate group. This one is named after two scientists, Friedel and Crafts. So this is called Friedel, Crafts, and we're going to add an alkyl group. Friedel, Crafts, alkylation. To do this, probably the most useful reaction using Friedel, Crafts, alkylation is to add a methyl group. So to add a methyl group, you're going to add CH3Cl. It's always going to be chlorine. And the catalyst is now AlCl3. It's like FeCl3, but the preference is to use aluminum. Your product is this. I'll draw it to the left. Does this look familiar? In Unit 13, we showed you how to do reactions at the benzylic carbon. So now you could put a bromine here. You could oxidize it to the carboxylic acid as well. Okay, again, we're trying to connect. Those Unit 13 reactions sort of seem kind of out of place. Like we didn't do anything with them. We didn't do any synthesis. We didn't see any mechanisms. But those reactions are going to be useful because we're going to pair them up with reactions in Unit 14 to get from benzene to a lot of different substituted benzenes. Okay. The last one, number 5. Also named after Friedel Crafts. But now this is Friedel Crafts. I'll just put FC. Acylation. Acylation. An acyl group is another name for a carbonyl group. Carbonyl. How do we do that? Let's add this acyl group. Okay, acid chloride. You've seen this already before, but not in this context. Friedel Crafts, for the vast majority of Friedel Crafts reactions, whether acylation or acylation, you want to use AlCl3 as the catalyst. Those of you who are doing the lab, not lab 5, but lab 6, you're going to be doing another Friedel Crafts alkylation without this catalyst. Okay, don't worry about that. Where do you think the point of attachment is going to be? You know that we're going to have benzene. Okay, it's this carbon here. Just like for the alkylation, you're attaching the ring to the carbon that's connected to the chlorine. Over here, the carbon connected to the chlorine is this acyl group, or this carbonyl group. I'll draw it to the right. Those are your 5 reactions for Unit 14 for now. I think I might add more, maybe. But right now, these are the most popular 5 in benzene reactions. This has a special name. All of these are called EAS reactions. What's EAS? Electrophilic Aromatic Substitution. Okay. Let me double check. My timer's gone for the recording. Let me just make sure I'm still recording. I'm still recording. Electrophilic aromatic substitution. You have an aromatic ring, and you're substituting that hydrogen for any of these 5 groups. But why electrophilic? For each of these reactions, you're adding something to the benzene ring. You're not adding a nucleophile, you're adding a electrophile. So the benzene ring is the one that's electron rich, the nucleophile, and it is attacking some reagent to add the electrophile. So these reagents are going to give us an intermediate that's electron deficient, right? Electron rich attacks electron poor. We're going to see that in the mechanisms. Okay? So let's do bromination first. Reaction 14A. Oh, since we could do chlorination as well, we'll call this halogenation. Bromine or chlorine. There are ways to add fluorine and iodine, the other two halogens, but you wouldn't do it this way. As a reminder, we have a benzene ring. Let's do Cl2. Cl2. And what is your catalyst? FeCl3. The product is chlorinated benzene. Okay. So you could do this with chlorine or bromine. We're going to do this with chlorine. We have to make the electrophile. For every one of these 5 reactions, you have to make the electrophile, and then you're going to use the benzene ring to attack it. Like I said, benzene, you need some special conditions to get it to react. So this is how we're going to make the electrophile. You have Cl2, and it's going to look a little strange, but we have this FeCl3, and we're going to make a complex. You could shorthand it as a condensed structure. FeCl3 is called a Lewis acid. We didn't talk much about Lewis acids. We talked more about Bronsted-Lowry acids, right? Molecules that donate a proton. Bronsted-Lowry bases are molecules that grab a proton. Well, Lewis acid and Lewis bases don't depend on protons for the definition. A Lewis acid is a molecule that can accept electrons. So you could call it an electron pair acceptor. Okay. It's identical to our definition of an acid. If an acid donates a proton, isn't it being bonded to the base by a lone pair? So this follows the definition also for Bronsted-Lowry acids. Okay. Think about what I like to think about is this reaction here, a reaction that you're very familiar with. Ammonia plus HCl. So we know that if I draw these two arrows, we know that this is the acid. That's the Bronsted-Lowry acid. It's the molecule that gives up its proton. But it's also the Lewis acid because it accepted this lone pair. It used this lone pair to make a bond to hydrogen. So it's a little bit subtle, but every single Bronsted-Lowry acid is also a Lewis acid. And I only talk about this example just in case I forget if this is an acceptor or a donor. I just look at a very simple example and say, oh, the acids are the acceptors of the lone pair. That was a lot of talk to prove that this happens. And that's all that happens in the first step. Look at the complex we have. The iron attained more electrons. This is going to be negative. The chlorine. Do you remember your formal charge equation? Valence electrons minus sticks plus balls. So halogens have 7. We have 2 sticks. 1, 2, 3, 4. We have 4 balls. So that's 6. 7 minus 6 is positive. Whoa. This is one of the rare cases where a halogen is positively charged. This chlorine on the end is neutral. We're going to call this the electrophile. So if I ask you, what is the electrophile for this reaction, you're not telling me Cl2, you're not telling me FeCl3, you're telling me this complex. So I'm going to put here equals E plus. Okay. So I know that this is net neutral, but what I'm saying is that this molecule will attract the electrons of benzene because it's a good electrophile. Okay. So how does the benzene attack this? We have our electrophile already. We're going to use one of the pi bonds to add what? To add a chlorine. And let me use this one that's closest. What chlorine are you going to attack? You are actually going to attack this chlorine right here. That's a little bit counterintuitive, right? Normally you would say, well, why don't I attack the positively charged chlorine? If you do that, then that chlorine will have too many valence electrons. Okay? Because if I attack this, it's almost like you have attacking a chlorine on a leaving group. Because now you're going to do this arrow here. And you're done. You're done with this step. So based on my pink arrows, can you draw me the result? The pi bond was used to make a bond to chlorine. And I'm going to draw that bond. Where am I going to draw that? I'm going to draw it right here. It didn't matter. I just wanted to try to space it out so it's a little bit neater. But this carbon is naked, right? It only has one hydrogen. So now in this case, it only has 3 bonds. You have a plus charge here. Oh, that's interesting. We lost aromaticity, but we're only going to lose it temporarily. What about the FeCl3 part? Well, now it looks like this. Fe. We still have one chlorine to the left, and I'll draw them out. It probably was unnecessary to do that. But we have FeCl4. That iron still has 4 bonds. That iron is still negative. Okay? This has a special name. This is called the rhenium ion. And for all 5 reactions, you will form what's called the rhenium ion. Okay? A fancy word for aromatic is also arene. Don't ask me why. But you could have molecules that are arenes, and it means that that molecule is aromatic. Not this molecule. This is the rhenium ion. But you could consider benzene an arene molecule. Or chlorobenzene an arene molecule. We gotta reestablish aromaticity somehow. You know which hydrogen to remove? This kind of drives me nuts. When the student knows that you gotta remove a hydrogen to get the double bond here. Are you gonna remove this hydrogen here? Or are you gonna remove this hydrogen here? Well, look at your product. It's the carbon that's attached to the chlorine that's missing the hydrogen, right? So you have to remove this hydrogen. How are you going to do that? There are a couple ways to do this. We're not going to make any assumptions about the solvent. The other thing is that this is a catalyst. Let me write that down, actually. Catalyst. What do we know about a catalyst? In the process of the reaction, you can consume a catalyst, but you need to produce it at the very end, because catalysts operate by adding just a little bit. So you need to regenerate it every time you use it. So we used it in the first reaction, or first step. We got to regenerate it in the last step so it could do its thing again for the next molecule. Right? So just like an enzyme is a catalyst, that enzyme doesn't get destroyed. Just like this FeCl3 doesn't get destroyed because we're remaking it. How do we do that? We need FeCl3. not FeCl4. So the way to do that is make a bond between chlorine and hydrogen, get back FeCl3, and now we're doing an elimination, right? Anytime we did an elimination, wasn't it a beta hydrogen elimination? What do I mean by beta hydrogen? Isn't this the alpha carbon? Remember, with elimination, this is the alpha carbon. And you have to eliminate a hydrogen next door to get the double bond to exist right there. So this is the beta carbon, actually. Not a big deal. Just understand, what are you trying to make? Which hydrogen are you trying to lose? Look at our result. Our result is this chlorobenzene. We created HCl, but now we have FeCl3. And that can start the process over again. That's the catalyst. You only need a little bit of it because it could do the reaction over and over again, because overall, a catalyst is not destroyed. It's not destroyed. One step to the electrophile. At the electrophile, reform aromaticity. Those three steps are the basic steps for all of these EAS reactions. Make the electrophile, attack the electrophile, reform aromaticity. That is halogenation. Let me do nitration. What time is it? Before we do nitration, let me list those steps. You have to make the electrophile. I'll abbreviate it. And then benzene attacks the electrophile. So benzene is acting as the nucleophile. And then number 3, we regain or reestablish aromaticity. I'll say regain. Aromaticity. Very interesting process. Let's do nitration. Now the thing is, to make the electrophile could involve more than one step. And I think we'll see that with nitration. Reaction 14B. We have benzene, and you're going to nitrate it with nitric acid, HNO3. And we're going to help make the electrophile by adding sulfuric acid. And we'll see what that does in just a bit. We add a Nitro Group, NO2. This is a nitro. You've heard of the explosive TNT. That's trinitro toluene, TNT. You know, toluene is the molecule with a methyl group. And if you're able to add 3 nitro groups onto that ring, you've effectively made an explosive. It's kind of very dangerous, actually. If you start out with toluene, the benzene with a methyl group here, there's been instances where in a waste container, someone accidentally puts toluene, a common solvent. You'll work with toluene in the lab, and then it's a waste container, so they put other stuff, and they put nitric acid. You're effectively making a bomb in your waste container. Now, hopefully it's dilute enough that you don't make enough TNT when you have toluene and nitric acid, but it's a very dangerous proposition. I've seen glass containers explode waste glass containers, because people were not keeping track of what waste they were putting into that glass bottle. Anyway, Before we get to the mechanism, you want to know, and we mentioned this in Unit 13, you want to know that the nitro group actually looks like this. The nitro group has formal charges, a plus and a minus. But overall, that group is neutral. But the plus right next to the ring is going to be very important when we talk about when we talk about adding more groups to the ring, more than one group. So nitration. Nitration, it looks like this. Start out with nitrate. What's nitrate? Do you remember that from General Chemistry 1? Uh-oh. Oh, yeah. No, that can't be right. Um, we're not making nitrate. We're making nitric acid. So I want to keep this hydrogen right here. Okay. So this is nitric acid. And then we're going to add sulfuric acid. We're not going to protonate this oxygen right here. In the mechanism, or in the round bottom flask, yeah, this gets protonated, but nothing happens, and it gets deprotonated, because this is a very strong acid. The productive set of arrows is protonating this oxygen right here, and you'll see why in the next step. We can abbreviate this part of the molecule as H2so4 minus. Right, we lost the hydrogen. But look what happens to our nitric acid. Our nitric acid now has a very good leaving group. Go ahead and copy that. We converted OH to water. Once a little bit of this gets protonated, it won't go backwards because the next step happens like a shot. So this is a reaction where it takes several steps to make the electrophile because we're not there yet. But what's the result here? The result here is very interesting. NO2 plus. NO2 plus. Plus water, right? We keep that water. That looks like a great electrophile. This is the E plus. That molecule right there. You can probably tell, oh, that's great. That is what I'm adding. I'm adding NO2. 2 steps to the electrophile. The last 2 steps, you know already. Benzene attacks, regain aromaticity. How do we lose that hydrogen? Okay. Benzene attacks. Okay, yeah, we will attack now directly the positive atom, but that's fine because we could get back the octet number of electrons by doing that. Right? That nitrogen satisfies the octet rule even when it's positive. And we have this. It doesn't matter which carbon you put the nitro group on, either the 2 o'clock position or the 4 o'clock position. I'll go with the 2 o'clock. I'll draw out the Lewis structure. Okay, we have one of these as minus, this is plus. This is your uranium ion right here. Which hydrogen do you remove? You remove the hydrogen that is on the carbon connected to the group that you just added. You made water. Okay, so nothing fancy. Let's use water as the base. And we get this. And that's how we regain aromaticity. Let's see. We also created acid, right? H2O plus. Right. So if we need something to pronate this oxygen for our next round, we could use more sulfuric acid, or we could use H2O plus. But there's your final product. Again, you make the electrophile, benzene attacks the electrophile, and remove the hydrogen to regain aromaticity. We are going to skip the mechanism for sulfonation. But just like I want you to know, and it's important for you to know, that the nitro group looks like this, let me go back to the roadmap and just draw out the sulfate group. Everything's neutral, but sulfate has an expanded valence. Not a big deal. The big deal later on that you'll see in the videos is that that sulfur is very partial positive. That sulfur is very partial positive. This nitrogen is positive. Whenever you have a positive atom next to the ring, that's going to affect how you add the next group. So you could already predict that we're going to get a little more complicated because, or a little more sophisticated, because we're not just going to add only one group to benzene, we're going to learn how to add 2 groups, 3 groups. It becomes very interesting because where do you add that second group? Do you add that second group next door? Do you add it 1 house away? Or do you add it 2 houses away? But again, that is quite a bit in the future. I want to get through today the Friedel-Crafts mechanisms, alkylation and acylation. Reaction 14C. Alright, I know some of you are fading. I am too. This is all recorded, so if you need to take a break, I can stay around for the notes, but if you're doing your review, make sure you take a break before you come back to this video. Friedel-Crafts alkylation. The name says it. We're adding in an alkyl group. Again, lab 6 is going to be a Friedel-Crafts alkylation. I haven't posted that lab 6 just yet. I'll probably do that today. Friedel-Crafts alkylation, we're going to start out with benzene. And our example, we used methyl chloride, chloromethane. Here, I'm going to do another example. Let's use chloroethane. We could alkylate with chloroethane as well, AlCl3. You're going to attach the ring to the dot, the carbon that's attached to the halogen. So here's your dot. Okay. It doesn't matter. If you thought you attacked this carbon here, you get the same product. It's just the wrong pathway. AlCl3 is just like FeCl3. It's a Lewis acid. And we saw what Lewis acids can do for us. In our first reaction, Lewis acid helps us make the electrophile. We're going to do the same thing. We have our alkyl halide. And we have our Lewis acid. Lewis acids accept lone pairs. And we're making a complex. Here's our dot. Okay. That's your electrophile. What we've been doing is we've been labeling the electrophile E+. Okay. In the mechanism, you don't have to do that. This is just a reminder. Make your electrophile, then your benzene can attack. What do you think is going to attack? Last time we saw Lewis acid didn't work. It attacked the atom next to the plus charged atom. And then we kicked out the leaving group. Right there. Okay. And then we kick this out. Perfect. We're going to add the dot and its methyl group to one of these carbons, and I will add it here. This carbon is naked. This is your plus charge. We're going to remove this hydrogen right here. How do we do that? Okay, so we kicked out this group, so now we have AlCl4. Let me show you the shorthand. Cl3, Al, and a bond. That's the same thing as AlCl4, but now all I'm worried about is using this bond to get rid of this hydrogen. And reform aromaticity. Ethyl benzene. And we reform the catalyst. AlCl3, good. And we created HCl. But what's important is you made the product and you reformed the catalyst. Very analogous to halogenation. Now, I need to do the acylation for photographs, and that's where we'll end. But I have to give a little warning about Friedel-Crafts alkylation. And there's going to be several warnings. This is the first one. For Friedel-Crafts alkylation, not acylation. For Friedel-Crafts alkylation, you can get a rearrangement. So this kind of sucks because we can't make a lot of different alkyl substituted benzenes using Friedel-Crafts alkylation because of this rearrangement. Now let me show you one example of this rearrangement. I'm not going to go through the mechanism. The purpose of this is to see how we can learn when to rearrange and when not to rearrange. This molecule right here, benzene. You can do Friedel-Crafts alkylation with CH3Cl, no problem. You could do Friedel-Crafts alkylation with a small alkyl halide, such as chloroethane, no problem. Right? You put the point of attachment where you expect it to be, on the dot. But when we get to 3 carbons, 1, 2, 3, and I'm hoping that I add a purple group, something bad happens. Okay? My target, according to what we've learned so far, is this. That's what we're hoping for, right? That makes the most sense. But actually, this is 0%. Okay. A very low percentage. What we actually get is this. I put a plus here, but technically you shouldn't even draw that molecule. Because your final answer will be this. We had a rearrangement. And the 3 carbons are now adding to this from the center carbon. And we'll call this the major. Okay? So we couldn't make our target. If I really wanted to make this propylbenzene, I cannot use Friedel-Crafts alkylation. Now, how are you supposed to do this? How are you supposed to predict this? I'm not going to show you the mechanism, but what you can think about is, do I have an alkyl halide that could potentially rearrange so we substitute at the more substituted carbon? The thought puzzle is this. You get rid of the chlorine, and you pretend that there's a carbocation here. You pretend that the benzene's attracted to the carbocation. But you know about carbocation rearrangements. We have a primary carbocation, theoretically, and you could shift a hydrogen or a hydride to make a secondary. So take your thumb, get rid of the chlorine, pretend there's a carbocation there, and then ask yourself, can I do one rearrangement to get the carbocation to be on the more substituted carbon? The mechanism doesn't work that way. That's just a mnemonic, a trick to get to the major product. Over here, it doesn't matter, right? Because if I cover up the chlorine and I say I have a primary carbocation, well, if I do any shift, I will still have a primary carbocation. So I will still make the attachment on one of these carbons, and it doesn't matter. It doesn't matter because it will be the same product. I hesitate telling you about this trick because at no time will we ever have a carbocation in this mechanism. Even in this mechanism, you don't actually have a carbocation in one of the steps. But you do have a rearrangement. Okay? I'm not going to tell you the mechanism because the rearrangement is a little bit tricky, but you are attacking now this carbon in the middle. You are attacking this carbon in the middle. Okay? That brings up an interesting dilemma because how do you make this then from benzene? How do you make this from benzene? That's going to be our next reaction. How do I make this? Because we're going to use Friedel-Crafts acylation, and this is reaction ABCD. Actually, the number got screwed up because I skipped the mechanism for this. So why don't I do this? We'll call this reaction 14A, 14B, 14C, 14D, and 14E for the 5 EAS reactions. So that's going to change actually this. Sorry about this. To 14D. 14C is the sulfonation, but we're not doing the mechanism. So 14E, the 5th reaction, the last reaction we'll do today. Friedel-Crafts acylation. Let me do something that's going to be useful to answer this question here. How do I make this? The acyl group I want to use is this acyl group, or the acid chloride, AlCO3. Remember how I said you're going to make the point of attachment to the dot? In this case, it gets a little screwy because of rearrangement. The beauty of acylation is that there's no rearrangement. So we're able to get 3 carbons in a row by using acylation. See, I could not do that. I could not add 3 carbons in a row doing alkylation. It would rearrange into this branched. To go from here to here, you need that reaction that gets rid of the carbonyl group. It has 2 different names. From here to here, you could do a Clemmensen reduction, or you could do a Wolff-Kishner reduction. That's why acylation is so great. There's no rearrangement, and you could easily get rid of the carbonyl group. This is a note, no rearrangement. Okay, we're almost done. Let me show you the mechanism. The mechanism is very interesting. It will also tell us why we don't get rearrangement. So yes, you're doing the same thing with that Lewis acid. You're making that complex. Plus charge right here. 2 lone pairs. Minus charge right here. Normally this is the time where you would say this is the electrophile. But not in this case. In this case, something's kind of neat happens. We're going to have this leave on its own because we're going to form a very stable cation. It's going to leave on its own. And we get this cation right here. Something that we've never seen actually. A positive charge on a double bond. We did get AlCl4, which you could probably imagine is going to help us deprotonate at the end. But I'm interested in this right here. This is called the Acylation ion. Acylation ion. It is especially stable because it has a resonance. And the resonance is going to look even weirder. So I want you to draw me the result of that mechanism arrow. Make sure you show your lone pairs. That will help you out. But definitely you have to show a positive charge somewhere. You have to figure out where that is. Alright, go ahead and take 30 seconds to draw me the result. Look what we get. We get a triple bond. Strange, strange, strange. And we have a plus charge now on this oxygen. Strange, strange, strange. Does that oxygen fit the octet rule? 2, 4, 6, 8. Yeah, it does. This is actually the major contributor because you know that carbocations do not fit the octet rule. This is your electrophile. This is E+. Because of this resonance and the stabilization, your molecule does not want to rearrange at all. Even if you had a tertiary carbon right next door, it's not going to jump. That plus charge is not going to jump to the tertiary carbon. You're not going to do any rearrangement. No rearrangement. And then you know what happens next. Beautiful. Because when I attack this carbon and I shift this pi bond back up, I basically have the product. All I need to do, right? All I need to do is remove that hydrogen right here. Right? Do you see how this is a result? This is a result of these two mechanism arrows. Get rid of this hydrogen. Oh, don't forget this plus charge, or else I'll take off a point. Your rhenium ion always has that plus charge there. I alluded to that we're going to use this as the base again. What's the shortcut? Cl3, Al, Cl. Minus. Grab this H. Collapse this bond. Make it clear. Some of the drawings on the exam were a little bit tiny, but I think I was able to interpret them properly. But look at that. We have 3 carbons in a row. We created HCl and AlCl3. Before I get to our announcements, end of lecture announcements, let's go back to this question. How do I make this from benzene? You take your acylated benzene, and this is your answer. Let me use Wolff-Kishner. A reaction that we reviewed in Unit 13. That's your first synthesis. The first synthesis is how to get benzene, how to make benzene into propylbenzene. And you do that by first Friedel-Crafts acylation to make this, and then you reduce it with Wolff-Kishner or Clemmensen. That's a 2. H2 and H2. Alright. I know that was a lot. Those are the only mechanisms that I need you to know for Unit 14. Okay. What is the rest of Unit 14? The rest of Unit 14 is how do we add more groups? And where do we add that second and third group? Then after that, you can imagine, whoa, we have a lot of potential synthesis because now I'm going to give you benzene and ask you to make a whole bunch of different molecules with different groups along the ring. So that is the topic for the next couple of videos. These notes have to be included in your video notes check. Just as a reminder, but again, you guys emailed me all the due dates. Okay, you guys emailed me all the due dates, but let me just double check, and then I'll let you guys go. Give me 1 second. For today, right? Today's Wednesday. You had your notes checked today. Oh, there's nothing due today. Thursday. 9:30 a.m. Your lab 5 stuff. Okay. Due. And then Thursday, 10 p.m. Tomorrow. Unit 14 notes. Due. On Moodle, there are notes. What I'm going to do if it's late, I think it's either half credit or some deduction, but try not to be late, or there will be a deduction. So these are your next 2 due dates. So give me some time to put up your Unit 14 videos today. Looking ahead, your Lab 6 will be due on Saturday, technically after the semester's over, because I want you to really focus on Exam 4. Exam 4 on Friday. Last thing, Thursday we do have a Zoom class, not mandatory, but it will be very helpful. So while this is due on 9:30, we have a 10 a.m. Zoom. Okay. Good practice. It'll be mostly Unit 13 practice doing these reactions on the roadmap, and maybe something a little bit new that will be in one of the early videos for Unit 14, either the second or the third video. Okay, so yeah, by the time 10 a.m. tomorrow rolls around, I'm hoping that you've seen at least 2 more videos for Unit 14, and that's my priority to try to get them out by this afternoon. Okay. Are there any questions or comments? I know this was a long lecture, but again, you don't want to lose any points for being late or for missing any important information that's going to be on the exam. All right. If there are no more questions or comments, keep working on those Unit 13 problems. I'll get the next video up as soon as possible this afternoon, and hopefully I'll see most of you tomorrow, and we could get reorganized to figure out what to do in those last, 24 to 36 hours before your final exam 4. Okay. Okay. I'll put up the office hours on Moodle in just a bit. See if you could find Jose either today or tomorrow, and I will see most of you hopefully tomorrow at 10 a.m. Big work day today and tomorrow.